Observe the operating systems running the world's infrastructure. They are massive, entangled structures where every piece of data feeds into a single, bloated central core. It is an architecture optimized for extracting and controlling information. This method of processing information at scale follows a trajectory starting with the International Business Machines Corporation, IBM. This is a document from the Auschwitz concentration camp in 1942. It was processed using IBM's Hollerith punch cards. These cards were explicitly designed to tabulate human traits, track locations, and organize millions of people into a centralized database for the Holocaust. CEO Thomas Watson micromanaged this operation from his office in New York. IBM leased the machines, serviced them on site, and remained the sole source of the custom punch cards required to run them. Corporate entities profit when they can provide the tools for centralized tracking. Architecture dictates behavior. When a system is designed so that a single privileged process manages every resource and every byte of data, the users inside that system are effectively confined. In the 1980s, a counter-movement emerged. Programmers like Richard Stallman identified the danger of corporate-controlled software and proposed a free, decentralized alternative. They championed a microkernel architecture. Instead of one massive block controlling everything, the system is broken down into small, isolated servers. No single program holds absolute power over the machine. Researchers at Carnegie Mellon developed a microkernel called Mach to handle the absolute basics, and the GNU project began building the HURD, a collection of independent servers designed to replace the traditional Unix kernel. The HURD was a moral effort to prevent centralized digital tyranny through engineering. By separating privileges and isolating processes, they were writing code that could not be easily weaponized against its users. Because a microkernel keeps every component locked in its own isolated room, these components must constantly talk to each other to function. If a program wants to write a file, it must send a message across a boundary to request permission. This communication overhead is called inter-process communication, or IPC. In the early 1990s, computer hardware lacked the processing speed to handle thousands of these permission messages every second. The system choked. The technical bottleneck turned the project into a decades-long grind. Progress stalled as the creators tried to force an elegant mathematical theory onto inadequate silicon. The toll was heavy. Thomas Bushnell, the original architect of the HURD, eventually abandoned the project and the digital world entirely to take a vow of silence as a monk. The hardware of the era could not support the vision. The pursuit of architectural purity failed because 1990s processors could not process isolation fast enough. While the HURD stalled, a student named Linus Torvalds released Linux. It was built quickly and served as a functional alternative to the stalled microkernel project. Linux used a monolithic design. It bypassed the communication bottleneck by putting all operations into one dangerous, entangled space. Data moved instantly because the protective barriers between programs were removed. Corporate giants, including IBM, recognized a structure they could back. They aggressively funded Linux's development, providing the resources needed to scale this monolithic model of control. This funding permanently established Linux as the default for modern computing, effectively ending the conversation about alternative architectures for 30 years. We traded security and isolation for the immediate convenience of a corporate-backed system. But the GNU HURD never died. In 2025 and 2026, the community achieved breakthroughs in 64-bit and multi-core support, proving the project was still viable. While Linux dominated the industry, microkernel theory evolved through projects like L4 and Sherry, waiting for hardware power to catch up to the math. Now, the hardware is here. Intel's memory protection keys allow the processor to tag specific regions of memory and validate access in a single clock cycle. Hardware-enforced isolation no longer requires a performance sacrifice. SexOS is the realization of the original GNU dream. It is built natively in Rust to leverage these new hardware capabilities, enforcing isolation at the level of the CPU itself. The technical barriers of the 90s are gone. There is no longer a technical reason to maintain a monolithic status quo. The difference is quantifiable. Because it removes the bloat of a monolithic kernel, the SexOS microkernel is exactly 96 times smaller than Linux. By utilizing lock-free communication, SecSauce operates 4 times faster than Linux. It provides hardware-backed isolation without slowing down the machine. This architecture removes power from centralized entities. By enforcing mathematical isolation on every application, it ensures that no single program can survey or control the entire system. SecSauce demonstrates that a decentralized system is a superior reality. It proves that the monolithic model is no longer necessary for performance. 36 years after the project's inception, the technical barriers have been cleared. SecSauce brings the original microkernel theory into a high-performance reality, dismantling a legacy of centralized control and securing the decentralized digital future.